Hello, this video was created by the student requesting some help on a particular problem in the Gen Chem course. So we're talking about the quantum mechanical model of the atom, and in order to explain the quantum mechanical model, we have to understand line spectra. And so this particular problem, you have an energy level which is labeled E, and then you have another energy level labeled D, and then you have another energy level labeled C. Okay. So we assume that the nucleus is here. We're going to assume the nucleus is here. And you say, how did you do that? Well, there is an axis, the y-axis here, and the y-axis says energy. And so we're going to assume the energy goes up this way. And that's maybe part of the problem, but that's the assumption. There's no clarification on the problem other than that. And so we're going to assume that. So the first question is which of these is the ground state? So the ground state is where the lowest energy for the electron resides, and that's going to be closest to the nucleus, so the nucleus would be here. So that would mean the electron is here. So E would be the ground state. Okay, and then the next question is, how many excited states are there? Well, if the electron is here, or the electron is here, we use an asterisk to represent that, there are two other places that are called excited states. So there would be two, D and C. Now, how many lines of absorption are in the spectrum? So what they're saying here is absorption means the electron absorbs energy, and when it absorbs energy from the ground state, it is promoted to the excited state. And it can only be promoted to either D or C. It cannot be promoted anywhere in between, and that is the quantum mechanical model of the atom. So that's why this is important. This shows you that the electron is quantized. It can only exist at E, D, or C, but it cannot exist anywhere else. So the absorption would be from your possible choices are E goes to D, E goes to C, or once you're at D, you could go from D to C. So there's actually three possible absorption lines: E to D, E directly to C, or E to D and then D to C. So there are three there. Three absorption lines. And I find students kind of miss this sometimes because it's about patience and really looking at it and not just trying to zip through the problem. You need to draw it out. You need to draw some pictures and think about what the possibilities are. And then, which transitions cause emission lines at the shortest wavelength? Well, that comes back to this equation, E equals h nu, right? So it says which transitions cause the emission line at the shortest wavelength. So here's what we know. We have learned in a previous section that the speed of any wave is equal to the wavelength times the frequency. So the frequency is equal to the speed of light divided by the wavelength. So the highest energy, the shortest wavelength is going to occur at the, well, let's do it this way. Maybe this would be a better way to do it. So wavelength is equal to the speed of light divided by the frequency. And so the shorter the wavelength, the shorter this is, the higher the frequency. It's an inverse relationship. The higher the frequency, the higher the energy. So that's what they're wanting you to do, is look at these equations to make your decision. So the transition, they're talking about emission. So for emission, let's see if I can change the color here to highlight this. So emission is when the excited state electron falls back down to the lower energy level. So the electron could fall from C to D, or it could fall from C to E, or we could have it fall from D to E. So it could fall from E to D, and then D to E. So the largest energy transition is from C to D for emission. So emission means energy is being released. So when this electron falls from the higher energy level to the lower energy level, energy is going to be given off. And this is the greatest amount of energy. So the greatest amount of energy means the highest frequency. The highest frequency is going to give us the shortest wavelength. So the answer would be the emission from C to D. And then it says, which transition causes emission line at the longest wavelength? Well, this one's a little tricky because you might be thinking D to E, but actually C to D, this is not as much of a gap as D to E is. So for 5, you would look at this and say the transitions from C to D. Actually, I made a mistake here. This is C to E. C to E. And then it's C to D for that one. All right, so and I did it right. I mean, I drew it. This is the biggest transition right here from C down to E. So I hope that answers your question. So you're saying, well, I don't understand this. Well, here's what you need to do. In our book, which is it's Overby Burge, section 3.4, you need to read that over again. That part talks about these transitions, and then they label these transitions, like you find out any transition in a hydrogen atom from that ends with the electron resting at the second energy level. That's called the Balmer series, and that's listed in a table on page 89 in the book. So it's important that you understand this, because again, what we've done here is we've gone from an atom that looks like a pool ball. That was Dalton's theory, atomic theory. Then we went to the J.J. Thomson model, which said the electrons are dispersed in this atom like raisins in plum pudding. And then we had the Rutherford model, which says, hey, there's a solid center to the nucleus where the mass resides, 99.99% of the mass with the protons and neutrons, and that the electrons are somewhere around here like this. And then when we get into this chapter, once we're introduced to Planck's equation and his theory, and then Bohr, that's what you're getting out of this. This is called the Bohr theory. So the reason why we get line emission spectra, is that the electrons orbit the nucleus much like the planets orbit the sun. So it's called the planetary model or the Bohr model. And so each one of these circles represents one of these energy levels here. And so that's what this is all focused on the Bohr theory. Now, is that the theory we end up with? No. We find out through de Broglie, Heisenberg, and Schrodinger that we're going to we go to an indeterminate model of the atom where we don't know where the electron is all the time. We cannot predict mass and momentum, which is mass times velocity. So we cannot detect. I didn't say that. We cannot detect position and mass and velocity all at the same time. Or another way to say it is we cannot predict position and momentum of an electron at any given time. That the probability of where that electron is greater than the size of the atom. And so we get into probabilities of where the electron is, which gives rise to orbitals. So when you hear the word orbitals, we've gone on to a quantum mechanical model. And in that orbital theory, you have labeled orbitals of S, P, D, and F. That's what we're focused on in this class. So I hope this helps. I think the main thing to do here is you need to read the material more than once. I definitely think you have to read this material 3 to 5 times. I think the first time is just to kind of get a lay in the land, and then as each time you read it, you start to build a little more of what we've talked about in this problem, which leads you to then the quantum mechanical model and orbitals. Do those example problems, or at least follow those that's in the chapter, and then you've got your module homework. But I can't stress enough that you also need to do the odd problems in the back of the chapter. That gives you a broader range of all the possibilities of questioning that could be done on an exam. So I hope that helps. And if you've got more questions, just email me. Thank you.